All right, good morning, everybody. I'm going to apologize in advance because I have a bit of a cold today. Thanks, students, for giving me that lovely piece. So if I sneeze or something, or my voice is a little croaky during this particular lesson, I apologize. But anyway, today's lesson is going to talk about measurement and how we deal with numbers in science classes, and a little bit about how it's different than how we deal with numbers in a math class, for example. So this process, or dealing with numbers, is what we call significant figures. It's also called significant digits. So you'll hear me go back and forth between those two. But typically we call it sig figs for short, because significant figures is awfully unpleasant to use as a label. I don't know who came up with that one. So anyway, in dealing with numbers, as far as a science class is concerned, the biggest thing that you have to realize is that numbers in math are sort of imaginary numbers. They're just numbers that someone grabbed out of their head and decided to use for different types of problems. A lot of times the calculations in math problems come out pretty cleanly. And like when you plot points on a line, they always line up right on the line, that kind of stuff. But numbers in science are messier. The numbers that we use in science class had to come from somewhere. Typically they come from measurements that we're taking. We're measuring something's mass or taking its length or figuring out what its volume is with a graduated cylinder, something like that. So they're real numbers, and they deal with real pieces of equipment and real human beings trying to collect those things. So there's always types of error. And there's always bits of equipment that are sort of in between us as scientists and the numbers themselves. They're not just perfect numbers. So the problem is that when we use equipment, we're not using perfect equipment. Equipment can be better or worse, and we'll talk about that here in a little bit. But we've always got something that we're trying to take a reading from, even if it's just a scale where you're reading the number off, but even if it's a ruler or a graduated cylinder where you have to look really closely to try to figure out what that particular value is. And some of the equipment that we use is better calibrated than others. Not that that's good or bad, it's just different. And so, sometimes you can figure out how long something is in terms of, I joke about hands and feet here. Those old school, like how many hands tall is a horse? It works. It doesn't matter exactly how many centimeters tall this particular horse is. Same thing with feet. It used to be the King Henry's foot, so whatever. It was a decent enough unit of measurement that people knew what they were talking about. In science, though, as we get better and better with our measurement, we want to get better and better in terms of how we're reporting those numbers, and we use different equipment for that. So with this, when we're dealing with using equipment, there's a concept that I want you to understand, which is the concept of precision. Precision means something specific in science. A lot of times we use the terms accuracy and precision, or accurate and precise, as meaning the same thing, and they really don't. So the little dart graphic there is a really great way to think about the difference between accuracy and precision. Accuracy is really how close you are to an accepted value. Did you hit the target right on? Precision means how repeatable is your data? How close did you get your measurements to each other? So, if I had 5 of you going and figuring out the mass of a, container of beans, how close would the 5 of you be to each other? Versus if the scale is off, that may or may not be accurate. So again, the concept of accuracy and precision is a little bit different. We're going to assume that you're using your equipment accurately, like you're not making any mistakes with it. But the precision that you're going to get from your information is different, and it's based upon the equipment that you're using. Are you using a bathroom scale, or are you using a lab scale? Are you using a ruler, or are you using a micrometer, a really good type of a measurement equipment? So again, it's a little bit different. And precision is something that we really have to worry about in science with our numbers. So again, the type of precision that we get depends on the equipment that we use. By the way, I mentioned a micrometer. Here's a typical classroom ruler, right? And that's actually pretty decent. Millimeters are really small. We can get a nice precise measurement out of it. But for engineering, you'd want to use something like this, which is a micrometer. It measures thousandths of an inch. Trying to measure gauges of metal, or if you're building an engine or something along those lines. Bathroom scale is another good example. A lot of times this one in your house is good enough. I just kind of want to carry, how much I ate last night. Versus something goes down to 1, 2, 3, 4, 5 decimal places, 10,000ths of a gram. It's incredibly precise. They might use that in a medical field or an engineering field. A thermometer. Do we really just kind of care if it's hot or cold outside? Or do I really need to know if I've got a fever, if my fever is going up or going down? It just depends on what we're doing and what our goal is. So it's not that low accuracy or low precision material is bad. It just has a different role in our world in terms of what we want to use. And the stuff that we use in science classes, kind of medium precise. It's not super awesome like some of this crazy lab equipment is, but it's definitely better than some of your household equipment would be. So with this, this is a good example of using two different precisions of a same type of a tool. So here's two rulers. We've got a ruler on the left, which is in inches. Shameful, I know. Inches, why? And then the one on the right is on, believe it or not, tenths of inches, which is kind of weird to have decimal inches, but it's a little bit more finely divided. So it's the same object. When we measure these two things, depending on which ruler we use, we get a different level of precision in terms of our answer, in terms of our measurement to it. So what this looks like is when we measure it on the left-hand ruler, we can guess kind of that last digit. We know the first one, we count 1 inch. It's definitely not 2 inches. It's somewhere in between, maybe just a little shy of halfway. So that's why I guess maybe 1.4. That's my guess. You might disagree with me, and that's okay. The ruler on the right, which has more little sublines to it, I definitely know it's 1 inch. And then I definitely know it's some of these subdivisions, 1, 2, 3, 4 subdivisions at least. And then it's between the 4th and the 5th subdivision. So then we can argue about how far down this is. Is it 1.48? Is it 1.45? But it's somewhere between the 1.4 and 1.5 area. So we have different numbers of digits, different precision between our two measurements. On the left, we have 1 decimal place, or 2 digits. On the right, we have 2 decimal places, 3 digits. And this is what we call sig figs. So sig figs is related to the number of digits that we can get from our equipment. So our goldfish here, kind of a similar idea. The length of kind of a less precise ruler on the top and a more precise ruler on the bottom. Because we're using different equipment, we get a different number of digits, and that's what we call sig figs. So if we measure these two fish, the fish on the top, we would call it about 4.2 centimeters, assuming that these are centimeters on there, because it starts at the 3, and it goes 1, 2, 3, 4, and then just a little bit more than 4, definitely not, not halfway to 5. So it's between 4 and 4.5, somewhere there, so I guess 4.2. Again, you could argue with me and say 4.1, and that would be just as acceptable. It's probably not 4.4, though, because that would be close to that next line. If I looked at the bottom one, again, I've got all the little subdivided lines on there. I can see tenths now. So now I know it's not just 4, and it's not even 4.1. It's between the 4.1 and the 4.2 line. So I would call that maybe 4.15 or 4.16 if I judge it was a little bit over to the right. So again, this is the difference between sig figs. One's more precise, so it has more digits. And the rule with sig figs is the significant figures in a measurement are all of the known digits, the ones you can read directly off of the equipment, plus the last digit, which is always estimated. We would call that between the lines, or if it's directly on a line, you'd call it a 0 at the very end. It's on the line, 5.0. So again, that's what we would call sig figs. So we'll take a look at some examples of this as we kind of move on here. So there's a problem, is that if we just had measurements and we never did anything with them, it really wouldn't be a big deal. But we do lots of calculations with our measurements, and as soon as calculators get involved, calculators love to do math. And man, they will do long division out to any number of decimal places. And so it's important to make sure that when we calculate stuff, that our calculated answers don't look better than the measurements that went into them. So if we have kind of low precision measurements that go into something, and then we hit equals on the calculator, we get this number that's got like 18 decimal places, that looks like a super precise measurement or super precise calculation, and that's actually kind of a lie. So we're not really allowed to do that. So there's some rules for how we kind of figure out what we do and how we count this. It's a particular type of rounding that we have to do. I know you guys round usually by just kind of figuring out a good spot, chopping it off, great. But what we do in science is that we round our answers based on sig figs. So you look at the problem that you did, the measurements that you have, and figure out the least number of sig figs in your measurements, whether it's 2 or 3 or 5. And then your answer is only allowed to have the least number of sig figs. So it can't be any better than any of your measurements that went in. So again, when we're counting sig figs to it, you take a look at, okay, this number in my calculation had 2 sig figs, this number in my calculation had 3 sig figs. That would mean that my answer, I would have to round it to 2 sig figs, 2 digits basically, in my final answer. Take the least one. Again, no random rounding, you can't just cut it off where you want to. And typically we'll use the rule of the number 5 rounds up because the number 0 is at the bottom. So anyway, number 5 rounds up. So here's some examples of what sig figs look like. Here's our rules for counting them because it does get a little bit messy. I'm sorry, it's not my fault. But anything that's not a 0 is significant. So those numbers up there is pretty easy. Just count the number of digits that's on there. So 359 has 3 sig figs. 34,823 has 5 sig figs, etc. Those are pretty easy. When we have zeros in the middle of a number, they're also significant. So these are pretty straightforward as well. 205 has 3 sig figs. 1003 has 4 sig figs, etc. It's when we get to zeros elsewhere, at the beginning or at the end of a number. So zeros at the beginning of a decimal place number, a really small number, or zeros at the end of a large number is where things get really messy. So here's the cardinal rule right here. If you have zeros at the end of a number, and there's a decimal place somewhere in that number, then those zeros count. So these are examples of what I'm referring to. So the number 0.350 has 3 sig figs to it. The number 0.21000 means it has 5 sig figs. And the last one, and the one at the end, the number 810 with a decimal place at the end, looks really weird. You'd never do that in a math class. But that's how we write the number 810 with 3 sig figs to it. Again, as long as there's a decimal place there, a 0 at the end will count. So you can tell where I'm going next. Zeros don't always count. So zeros are just super frustrating because other zeros are just what we call placeholders. They're simply there to kind of hold the decimal place in its location. They're usually a result of kind of what unit I'm dealing with in terms of metric system, whether I reported something in kilometers or millimeters kind of thing. So there's some examples of some non-significant zeros. So the number 540 has a 0 at the end, but there's no decimal place. So that only has 2 sig figs to it. The number 0.00023 has what we call leader zeros. So leader zeros are never significant. They don't count either. And there's no zeros at the end, so the number 00023 has 2 sig figs to it. The number 8020 has 3 sig figs to it. The 8 is significant, the trapped 0 is significant, the 2 is 0, but the 2 is significant, sorry, but the last 0 is not. Again, there's no decimal place there, so it does not count as being significant. I need to blow my nose, I'm sorry, pardon me. And then the last one, 0.01, again, those are leader zeros. Leader zeros are not significant. So it's a little bit of a weird process dealing with zeros. Again, trapped zeros are always significant, and then zeros at the end, if there is a decimal place, are significant, but anything else does not count. So here's 3 examples for you, and I'll let you take a look at these for a second. Hit pause, see if you can figure out which, how many sig figs are in each of these values, and I'll come back and highlight them for you in just a second. You ready? All right, so here they are. So for the number 602000300, all of these would be counting as significant. These 2 zeros are trapped, so they count. These 2 are at the end of a number that has a decimal place, so they count. So that has a total of 1, 2, 3, 4, 5, 6, 7 significant figures. The next one down, this one right here only has a total of 5 significant figures. Leader zeros never count, so they are not significant. I know it's weird. The 1 counts, the trapped zeros count. The 5 counts because it's a non-zero, and this one at the end counts because there is a decimal place somewhere in there, so that trailing 0 still counts. So that's a total of 5. Now the last one, 30,000 or 30 million, this only has 4 sig figs to it. There's no decimal place anywhere in this particular value, so those ending zeros, the trailing zeros, do not count in this particular case. Total of 4 sig figs. I know, it seems really random. I promise you there's reasons for it, but it is kind of frustrating. So here's a couple of calculation problems for you. Again, remember the rule is that your final answer has to be rounded to the least number of sig figs that are shown in the measurement. So in this particular one, we're talking about the volume of this object. Remember, volume is length times width times height. This number has 4 sig figs. This number has 3 sig figs. And then the last one has 3 sig figs as well. There's a decimal place, so that 0 counts. So that means when you calculate this volume, your answer can only be rounded to 3 sig figs, and you chop everything else off. Density down at the bottom, remember density is mass divided by volume, so you take the top number divided by the bottom number, and this one also only has 3 sig figs to it, because the mass has 4, the volume has 3 sig figs, so our answer can only have 3. So take a second to do these math problems, and then I'll show you what the answers are. So, you ready? Here we go. Okay, so the top one, volume. There's my calculator answer. Hopefully I didn't do any dyslexic weirdness to type them in funny, but that's what I got as a calculator answer. And that's what shows up on the whole screen. So all those numbers are great, but we can't use them all. Again, our problem here, we only have 3 sig figs to work with because 2 of our measurements only have 3 sig figs. So that means when we round this, we're going to round it to 3 sig figs. Starting at the 114, we count from left to right to get our significant figures. So our final answer is 114. No decimal places in this one at all. 114 has 3 sig figs, and the units for this, by the way, is cubic centimeters. For density, when I divide these 2 out, there's my crazy calculator answer with all kinds of decimal places to it. Looks amazing. But again, with this problem, we only have 3 sig figs to work with. So in dealing with this one, we finally round it down. We only have 3 sig figs. So we start at the beginning. There's the first digit. There's the second one, and there's the third sig fig. And then I have to look at the stuff after it. Do I round up or round down? So because this is such a big number, it's kind of a no-brainer that we round that up. So we get the final of 3.39 as our final answer for that. Okay, so here we are at the end. So what did we hopefully learn today? We took a look at the idea that our numbers in science are about measurement, and measurement always involves estimation. So that last digit is usually between the lines, and we got to figure out, kind of guesstimate where that last one is. So our equipment precision, the number of decimal places that we get off of it, is kind of due to the equipment that we're using and how good the lines are, so to speak. The sig figs numbers that we get is due to the measurements that we make. It's not a made-up number. It's actually related directly to whatever the equipment was that we used. And that our answers for calculations have to match those original ones. Our answers can't be better than the measurements that went into it. The last part, and I know it's annoying, is watch out for zeros. When you're counting sig figs, zeros are the crazy ones, and it's always the zeros at the end. Do they count or do they not count? So hopefully this gave you some insight. We're going to practice with these more tomorrow, and hopefully you're having a good day, and hopefully this cold of mine gets better, right? It's starting to sound really funny. All right, I'll see you guys later. Have a good day.